Hey Phys 1 kids, Campbell here. One of the most important things we do in physics, especially in lab, is analyze relationships through graphing. So this video is going to take you through the most common graph relationships we see in physics and how to transform those graphs, also called linearizing them, so that we can get information from them. Now, why do we graph? Why is this such a big deal? Well, it's a visual way of representing relationships between quantities so that we can figure out how, if we change one quantity, what's going to happen to that other thing. They're very useful because we can take a lot of data and put them into a picture that summarizes what's happening. You can't do that with just a data table. I mean, data table, you can look at the numbers, but trying to figure out exactly how the numbers are relating to each other as we change one of them, it's just not as easy to see. So when we collect data, because we will be scientists in our lab, we are going to do graphs to see how did those relationships relate to each other. And that way we will know, if I change this, what's going to happen to that? And it'll help us lead us to equations for physics variables. Now, the easiest relationship is the direct relationship. The direct relationship simply says that as y increases, so does x by a proportional amount. So our change in our variable 1, whatever is on our y-axis, is equal to some constant times the change in our whatever we've graphed on our x-axis. So we say that this is a direct relationship, and so from a proportional standpoint, we say that y is directly proportional to x. This is a proportional sign. It's sort of like an infinity sign or an extended alpha looking, but that's a proportional sign. So that means as y goes up, so does x. Now, if we write this as like an equality statement, which is really kind of what that change in variable 1 thing on the top of the page is, we would say that therefore y, whatever's on our y-axis, is equal to some constant, which I'm just going to call c. We'll just abbreviate that constant, times x. And mathematically, what that equation would be just a linear graph. And so what a linear graph would look like, right, is just a straight line. Now, I did not put this straight line at 0. Sometimes our lines will go through 0, sometimes they won't. That'll be something that we'll talk about when we talk about rules for graphing at another time. But the equation for this line is the equation you learned in your math classes, that y is equal to mx plus b, where x or m is our slope, right? And if we look at our equation right above that, y is equal to c times x, that slope represents that constant c. And what that means is, if you remember slope, right? Slope is rise over run, which would be our change in y over change in x, is the value of this constant. When I have a straight line, it's simple. I just plot the data, I calculate the slope, and I know what that constant is. And that constant usually has some physical significance in physics. Like if we have a position versus time graph, we'll see that the slope is the velocity, because the velocity is the rate of change of position over time. Now, b, of course, is my y-intercept. You should also know that from math. And sometimes we will have a y-intercept, sometimes we won't. Now, in this case, we have a linear relationship, so we don't have to do any transformations, because when we're doing these transformations, it's because we want to get the slope of the line. And here the slope is constant, so I am good to go. So direct graphs are really the best, easiest graph to work with because I don't have to do any transformations. So let's talk about the ones where we do. One of the common ones we'll see, especially in our first unit on kinematics, is a direct to square relationship. And basically what that means is as y increases, x increases by the squared amount. So what that looks like actually is this. This is called a top opening parabola. And basically what this is telling me is that as y changes, the x is going to change by a square. Why are you not writing well for me? So by some constant times x squared. What is wrong with you? X squared. So when you see a top opening parabola, our proportionality statement, the proportional relationship is that as y increases, then x is going to increase by a squared value. So y is proportional to x squared. Or from an equality statement, then y is equal to some constant times some constant times x squared. Now, if we look at this graph, right, this time the constant is not the slope of this graph, right? The slope is changing, so I can't get a slope. I could get like an average slope, but there's not much I can do with this. But it's because the relationship is x squared. And what that means is I can linearize this graph. I can magically make this data into a straight line by just doing a little bit of calculation manipulations. And so what this means is if I want to get the slope of this line, because the slope is significant in some way, I can linearize this by plotting the y value versus x squared. So I'll just square all my x values, I'll like make a new table, I'll plot the data, and then magically I'm going to get a nice straight linear line. So when you see a top opening parabola and I ask you information like, oh, what's the acceleration? Yeah, to do that, you gotta square your x values, which could be time usually if you're dealing with acceleration. And if you do that, you're gonna get this magically straight line. And so then our equation, then we got a simple equation, right? We're back to our linear y is equal to mx plus b. So now we have y is equal to our slope m, which is our constant c. But our x value isn't just x, it's x squared. All right, so there's our equation for our linearized graph. So that means if I get the slope of this and I multiply it by x squared, it's going to give me the y value. So it's really cool. And actually, we're going to do one of these together near the end. And you'll see magically we go from this top opening parabola to a nice straight slanted line. It's beautiful. Another relationship is the direct to root relationship. And basically what that says is that y increases, x increases by a square root. So what this looks like is different. This looks like a side opening parabola. And basically what this is saying is that as my x value is increasing, the y is increasing, but not directly proportional. It's plateauing. My y value we're reaching some sort of critical level for my y value. And so my proportionality statement, if you see a side opening parabola, what that means is that y is proportional, proportional to the square root of x. So side opening parabola, we're reaching a maximum value on the y-axis as we increase x. That means y is proportional to the square root of x. Or if I wrote an equality statement, that would be y is equal to some constant times the square root of x. But I can't just get that value, that constant value that I might need in some sort of graph interpretation. I can't get that from the graph that I have right now of y versus x. I actually need to regraph this. And so if I regraph this, I would regraph it as y versus the square root of x. And of course, if we take the square root of our x values and we replot it versus y, we're going to get this magically straight line, which is really cool. And then our equation for our line is y is equal to the slope, right? That's our constant c, times the square root of x plus b. So you see this relationship? Think square root of x. Now, there's actually another thing you could do to get this to be a straight line. The other thing you could do is this. You could actually square the y values instead. And plot it versus x. You'll get the same thing. So if you see this side opening parabola, this decreasing in the rate of change of y like this, that means if you replot as y versus the square root of x or y squared versus x, you will get a nice, beautiful straight line that you can use to get slope from, because I'm sure I'm going to ask you to figure out what the slope of the line is, because it's going to mean something from a physics standpoint. The last relationship is the inverse relationship. And what that means is that as y increases, x decreases, or as x increases, y decreases. Now, most people think of inverse relationships as actually slanted, downward lines. So a line that would, a slope that would look like this to you. But that's actually not the case. And I know you probably don't believe me, but what it actually looks like, and you'll see this when we do these graphs, oops, sorry, is that it looks like that. That is an actual inverse relationship. It's a positive half of a hyperbola. So this is an inverse relationship. It is not a straight slanted line. It is a curvy line. And what this means is that as our y variable is changing, so whatever we have plotted on the x value is changing by 1 over that value. And so our proportionality statement would be y is proportional to 1 over x. There's also a possibility, and I wish it would be easy for me to change colors here. This is another inverse possibility. That relationship, so this is my 1 over x value, that relationship would be steeper. So this would be a 1 over x squared relationship. But we'll just focus on the 1 over x relationship for now, that inverse relationship. Our equality statement then for our first one there is y is equal to some constant times the value of 1 over x. And so what that means is if I want to change this graph so that I get a straight line, so that c would be the slope of my line, I can plot this by taking my y values as they are, don't change those, and then just taking the inverse of all of my x values. If I replot it, I'm going to get a nice straight line where my equation would be y is equal to some constant c, our slope m, it's our c value, right, times 1 over x plus b if there happens to be a y-intercept. So one of the things you will see me ask you to do, and you'll see in physics problems, it'll say, how can you regraph this data, or how can you graph this data so that you can get a straight line where you can determine the slope of the graph. So it's very important that you can recognize what the graph looks like, how the y is changing with respect to x, or x with respect to y, and what that means in terms of the relationship. Is it a direct relationship? Is it a direct squared relationship? Is it a direct root? Is it an inverse? What is it? And then how could I manipulate that graph to produce that line? All right, we're going to actually take a look at some examples of what you'll be doing when we have graph relationships. So let's take a look at this most simple example. Here is a direct relationship. Graph this with distance on the y-axis and time on the x-axis. And so one of the things you'll have to do is calculate slope. Now, by the way, the line on this graph, you'll know it doesn't go point to point. It doesn't go dot to dot. Don't ever draw lines dot to dot. We'll go through that more in the rules when we talk about graphing rules. But our best fit line, which models the data, is what we're going to use to calculate slope. Now, never use data points to calculate slope unless they actually go through. So like we possibly could use this one, but I don't like to do that. And I suggest that you don't, because it's very important that the grader, whether it's me or the College Board when it's the AP exam, are going to be looking to make sure you know this. So I'm going to pick other points, and usually I like to put points where it crosses through an intersection, but unfortunately that's not close enough. I don't see any that do that. So I'm going to pick this point right here because it's kind of like in the middle of here and it's on this line. And then to calculate slope, I need another point, and since this happens to go through 0, which is kind of a miracle, it usually doesn't, I'm going to use this for my rise over run. And I like to actually even kind of make a little triangle here. My rise, right, this is the change in y, so this would be 3.25 minus the bottom value, oops, that's supposed to be a 3, 0, and here my run, right, it goes 2.5 minus 0. So when I calculate my slope, right, that would be that 3.25 divided by the 2.5, and again, if that hadn't been 0, it would have been by some number, and I get 1.3. Now, anytime you do a slope, make sure you include units. So the y values, right, that change in y is on top, so that's the meters, and the unit for the time is seconds. What does the slope represent? Well, if you think about it, the slope represents how far I'm going for each time interval, which represents how fast I'm going, and we call that speed. Right? Speed is how fast you're going. Or if this was displacement over time, we call it velocity. And if we wrote an equation for this relationship, right, if I called d what's the distance, d, which is on my y-axis, we'd say that the distance is equal to the slope, which is our 1.3, our constant, times our x value, which is our time. And that means that any time, then if I want to know how far I've gone, if it was an hour from now, right, I'd convert that to seconds and I'd multiply by 1.3 and I know how far I went. So using slope allows me to calculate other values, and it also tells me things like how fast am I going. So simple relationship. More complicated relationship between distances and time is a direct to square relationship. And we'll see this, especially when we have something called acceleration, which we'll learn about in our first unit. Now, here, I thought we'd go through the whole process of drawing the graph and then evaluating it. I already told you it's a direct to square, but we're going to see what that looks like. So here's a graph. So graph this with me. According to the table, when we've gone 0.1 seconds, we've traveled a distance of 0.045 meters. So if I go to my graph, that would probably be right around here. My next interval is at 0.2 seconds. I've traveled almost 0.2. So at 0.2 seconds, we're almost at 0.2. So I'm going to put another mark right there. And now we're traveling at 0.3 seconds. We're at just over 0.4. So we'll put another mark right there. And at 0.4, we've gone to 0.764, so just over half on this line here. At 0.5, we have traveled almost 1.2, so we're really close to this line right there. Oh, where did my 0.4 mark go? Sorry about that. Having some struggles here with this thing. And so now when we draw this relation, oh, we also have one at 0. I apologize, I didn't mark that one. When we look at this graph, we can tell that it's not exactly straight. It kind of looks a little bit like it, but it's definitely, we see a definite change in slope really at that bottom. So when you draw lines on your graphs, I'll either tell you to draw a best fit line or a smooth curve. So you have to decide, does this look like a linear fit? Does it make sense that it's a linear fit? I mean, it doesn't look like it's exactly a straight line. Or should it be a curved fit? Well, I already told you it's a direct to square, so it should be a curved fit. And so when we draw this, you're going to draw a smooth curve. Again, no dot to dot. We're going to draw a smooth curve, which goes through some of the points there. But a smooth curve up, and you can see that it has that parabola relationship, that top open parabola relationship there. So that would be a direct to square. So if you see a top opening parabola, I want you to think that about this: y therefore is proportional to x squared. So what we're going to do now is we're going to replot the data to see this magical transformation into a linear relationship. So what we're going to do is we're going to take our x values, right, which is the time values, right? These are the y values. We're going to take our time and we're going to square it. So that means our unit's going to be second squared. And so when we do that and we fill out our table here, of course, that's still 0. This is going to be 0.01. This is going to be 0.04. This is going to be 0.09, 0.16, and our last 0.5 squared is going to be 0.25. Now we need to make a new x-axis here on our distance graph. Of course, this will be a separate graph, so sometimes you will be making several graphs. And so when I do this, let's go 0.1, 0.2, 0.3, and 0.35 would be the end. Okay, so there is my time squared. And always label your axes. This is time squared, which would be second squared. So now we're going to go and replot all this data again. Of course, this is 0 here. And we have a 0, 0 point, so we'll put that in. Now at 0.01, which is going to be like right here, right? Because this is 0.05. At our 0.01, we have gone 0.045. So we'll make our marker right about there. And then at 0.04 seconds squared, we have traveled 0.187, so that's just inside here, and it's about right there. So let's make that mark. Our next interval is 0.09, so we're just inside this line here. And we're going to go up to just over 4, so that's about right there. Our next mark is 0.16, so we're just past this point here, and we're going to go up to 0.764, so just over our half here, so right there. And then our last point here is 0.25, and we go up to almost 1.2, so about right there. So now if you notice, if I draw a straight line, which is going to be really difficult because I don't have a straight edge, you should use a straight edge. You should carry a straight edge. You should have a straight edge. But if I draw my line, a best fit line is a line that models the points, that doesn't go dot to dot, but it should have about the same number of points above as below. So mine's a little off because it looks like these 3 points are above and I only have 1 below. But I'm hand drawing this. You should be using a straight edge. In fact, a transparent straight edge would be lovely. Now I want you to calculate slope from this. This goes through this intersection here. It's at 0.05. And this, let's say that this line goes through here. It doesn't quite, it's close, but I think that's just because of me. So here's going to be what I'm going to calculate. Of course, I could have picked 0, but I don't want you to think you can do that every time. So this point would be 1.4 right up here, because this is 1.2. That'd be 1.4 minus 0.2. All right, that would equal 1.2. And then my run here is 0.3 minus 0.05, which would be 0.25. So to calculate my slope, right, slope is rise over run. So we have 1.2 over 0.25 equal to 4.8. Ugh, 4.8. And again, pay attention to your units. This is meters over second squared. And so if we write an equation for this linearized graph, right, we would have our distance is equal to 4.8 t squared plus b, which is 0 because we have a 0 point there. All right. Look at the picture of the relationship. Then based off that picture, plot by changing the x values. So what you're going to do now is it's going to be your turn. So the next pages in this packet that you have the other physics relationships, the direct root and the inverse. So what I want you to do is to practice what you've learned. So complete this packet and we will go over it when I see you in class. So I will see you in class.